So good morning, everybody. And in this talk, I will speak about a general methodology to monitor, to visualize complexity in heterogeneous matter. Okay, I work in the Institute of Crystallography of CNR. And since let me start speaking about crystallography a little bit. One of the main goals of crystallography is the structure solution. And nowadays this is done in an automatic way. You have just to put inside your software package a list of measured Bragg reflection, and software give you the structure. And this is done for all the structure going from few atoms in the unit cells, for passing from macromolecular with hundreds of atoms in unit cells, up to proteins with thousands and thousands of atoms in the unit cell. In all this case, the procedure is quite automatic. But this procedure is based on an implicit assumption, and that is the space invariant of structure. Point by point, the structure is always the same, so you get the average of the information. And this is not perfectly true, because even in the perfect crystal, you get some defects. And the defects can be of various type and kind. And when the concentration of defects is quite low, the standard crystallography continues to work quite well. But when the defects overcome a threshold and the concentration is not too low, you have to take it into account, and we have to modify the theory of diffraction and to modify the structure factor, introducing two corrective terms. And when you dope material, as in semiconductor or superconductors, usually the defects are at high concentration in the material. So, and usually there is this synthesis that I like, that defects tend to make materials interesting as the people. And I would like to show you some example. This is a perfect structure where you have a lattice, perfect lattice. If you do X-ray diffraction of this simple structure, you collect a single spot, Bragg spot. No surprise. But if you modify the structure, for example, modulating it, introducing some interstitial atoms in a precise site, or you form local microdomains, or you add vacancies or interstitial atoms in a preferential direction, you get a feature in the diffraction pattern known as diffuse scattering. So in these cases, the standard tools of crystallography fail, and you get in the reciprocal space other features, strange features such like streaks, superlattice, reflection with reflections, or broad reflections. These are quite weak peaks, and usually are localized and so you need a high flux to detect this kind of feature, and so you need the synchrotron radiation to measure them. Okay. These are real measurements on superconducting systems. We have a lanthanum cuprate here. You can observe the strong, drag peak, and weak superlattice in the reciprocal spaces. This is the yttrium barium copper oxide, where we have segments, streaks, denoting the oxygen ordering in the lattice, and in the in the mercury cuprate, you get streaks crossing the bragg peaks in your diffraction pattern. All these features are due to the oxygen ordering and the defect ordering in your samples. And those crystallography and the X-ray diffraction is candidate to be a good tool, a powerful tool to study and to detect this kind of order in your sample. When you dope your sample with interstitial atoms, for example, you give your samples also charge carriers that can be holes or electrons, and these can be in patterns organized also in the samples. There was a Wigner in 1934 to claim that at low concentration of doping, electrons can be ordered in the lattice. And now we have a lot of experimental evidences, starting from Trancada, Biringhelli, and other scientists measuring this kind of weak reflection in reciprocal spaces associated to the crystal of electrons. Not itinerant electrons, but the crystals of electrons called the charge density waves. In the same way, you can also have a spin density wave or orbital ordering in a strongly correlated system. Okay, so what happens is that these local domains compete in the sample, but an important thing is that these domains you can pass. These domains have a spatial organization, and you can cross and pass from a spatial organization to another. And the energy of this different spatial organization is the order of millielectron volt. It is 2 or 3 orders less than the covalent bond in a crystal. So you get some kind of soft matter in your hard matter, and this makes a strange mixing and needing particular tools to be investigated. Well, our tools consist of synchrotron use, use of synchrotron radiation thanks to the brightness and the coherence of these radiations. We can use, thanks to the brightness of synchrotron radiation, we can focus the radiation on small spots, nanometer scale or micron scales, and in this way we can scan the sample, getting information not average in space but highly resolved in space. What we do is basically catch, explore the reciprocal space, because we don't need no more measure only Bragg peak, but we need we need a deeper investigation and deeper exploration of reciprocal space, getting this kind of strange feature, associating them to the, for example, oxygen interstitial dopants, or whatever, of electrons ordering or spin density ordering. Once we know this reflection associated with this order, the next step is to map the sample point by point. This is done by moving the sample under the beam, under a very focused beam, and in this way we get rich maps of the feature in the real space. So I would like to mention that, for example, as a mesh with 100 per 100 micron with a step of 1 micron give us 10,000 frames. And if we use the same, if we measure the same mesh, 100 per 100 microns with a step of 100 nanometers step, we get 1 million frames. So it opens a new problem of data storage. The last time we collected 20 terabytes uncompressed data, and I don't know how to take and how to manage all this data. Well, we need also software to analyze this data, and this software was done in our institute with collaboration of Alessandro Ricci. You can develop all your frame, you can select some feature, and you can map these and analyze this. And then once you analyze this, you use the spatial statistic tools to describe the disorder or the arrangement of the spatial organization of this sample using spatial probability distribution or spatial correlation, clustering, tessellation, and other tools of spatial statistics. Connectivity is another tool, is another characteristic to be used to characterize these systems. And this methodology I described can be used also for other systems, going down in scale, for example, system characterized by nanostructure or mesostructure or microstructure. For example, we can study with using the same methodology steel or cements or biological tissue as, for example, bone tissue or spinal cord and whatever. Well, I would like just to show you some application where we use this methodology. And the first case is a superconducting study of lanthanum cuprates that is doped by oxygen interstitials. And when you dope this system, you get the weakest satellite reflection between the strong Bragg creek, and this is due, as I told you before, to the oxygen ordering in the lattice. And I would like to repeat that you can manipulate this order because they have the energy of a few millielectron volt. A few millielectron volt correspond to a few degrees of temperature or illumination of light at a sample. So you can, in this case, we illuminated this sample with X-ray and we obtained the ordering of oxygen with this speaker. At the same time, we can manipulate it with the temperature by thermal cycle, or both X-ray flux and X-ray and temperature variations. And here we see two different hystereses, one with high flux and one with low flux. All these methods to manipulate the sample bring our sample in different state, different energetic state. And in this case, for example, we have two states in which we manipulated the local domains of the sample. And these two states, for example, has two different superconducting temperature. In this case, the sample is exactly the same. We just manipulated it with the thermal cycle and illuminating it. And this two state has a different probability distribution, where we have a power law distribution of the order. So it means it's related to a critical phenomenon, and we have a contraction on an expansion of the scale invariance into these cases. And we have also a different special correlations between the two samples. Well, this is another sample. This is another sample. Is a mercury cuprate, where we can measure both the oxygen interstitial defects, that are the dopants, but also the charge density waves. So we have, in this example, we can study both the oxygen ordering and the electronic ordering. We say that these two kinds of ordering has a different temperature dependence with different onset temperature. And we have seen, I've measured that the charge density waves in the sample is not homogeneous. This is charge density waves measured in seven different points of the sample, and you can see the different peak. And when you map with the X-ray micro diffraction both the charge density waves and the oxygen content, we find a power law distribution that describes both, and an anti-correlation between both. Where we find charge density waves, we don't find oxygen in the sample, and vice versa. And this gives rise to a complex geometry where these balls are the charge density waves, and the white space is the oxygen places, and so here are shown two possible pathways for the electrons for going from a point to another. Okay, in this example, in this example I show the biological study, another subject of study, but in which I use exactly the same methodology, and in tissue engineering, where stem cells are seated on top of a ceramic scaffold and implanted in an animal, and then after determined implantation times, the sample is extracted by the animal, from the animal and is analyzed. Here is a phase contrast image of a slice of the sample, the extracted samples. We can see three different materials: the new formed bone, an interface, and a collagenous matrix formed during the implantation. Now, this interface between the new formed bone and the soft tissue collagenous matrix is has a thickness of 20 micron. And those, if you want to study what happens at this interface, you need focused beam, of course, because with the laboratory beam, the best laboratory beam is large, 100, 200 micron. So you can't do a study of these features. And this is just to show you what in the technique, how it works. You have a mesh on your sample. You take a frame point by point, and then you need the software to classify your patterns, because you take point by point input profiles from collagenous, from a new formed bond, from the scaffold, and you have also a large range of Q, because in this way you can study in a small angle region the nanostructure, in the intermediate region the collagenous matrix of about 1 nanometer, and in the wide angle region you can study the crystalline property of the materials. In this way we have written a neural network algorithm to classify the different signals and analyze them in the different portion of reciprocal space, obtaining maps of the different characteristics, and in this way we can study the fluctuations of these characteristic at different scales. At nanoscale, we can take the collagen fluctuation, or we can take the nanocrystals of hydroxyapatite distribution, and that's the thing that gives to the material its mechanical properties, because the bond is just a distribution of nanocrystal in a collagenous matrix. And this is important, for example, for preclinical application in which a particular distribution of spacing of collagenous matrix can be associated to osteoporosis of other pathologies. This is a preliminary data, but interesting, because here we studied at cellular levels the biomineralization, and we see that this dynamics, strange dynamics, when stem cells deposited onto a support differentiated, becoming osteoblast and depositing nanocrystals, we have a particular morphogenesis of this differentiation, passing from an exponential distribution of nanocrystal deposited to a power law and scale invariant deposition, where we can get the aggregation, particular aggregation of this differentiation. We can skip about this one. And the conclusion is that above 10 microns, the fluctuation of structure above 10 microns are a classical issue of material of engineering to optimize material properties. But when you go down in scale, studying the fluctuation at the mesoscale, at nanoscale, can give you information on fundamental science for developing innovative material functionality. Okay, thank you. Thank you.
So we are moving from solid state to photons, and then finally we arrive to biology and medicine. There are some questions. Otherwise, we shift to the next talk because it's time is going fast.